Okay, good evening, everyone, and welcome. It's been an exciting 2 weeks here at Fermilab as we've watched the rest of the world wonder what G-2 is all about. So you happen to have picked a good night to come to a public lecture. It's my pleasure to introduce our speaker this evening. So it's Dr. Adam Lyon. He's an experimental particle physicist here at Fermilab. He received his undergraduate degree from North Carolina State University in 1991 and his PhD from the University of Maryland in 1997. He did his thesis work here on the D0 experiment, which many of you know, and searched for supersymmetric particles. And he did not find any. After that, he went to the University of Rochester and studied heavy quarks at the Cornell Accelerator. And then he came back to Fermilab and joined the scientific computing division as an associate scientist. He's been heavily involved in particle physics here at the lab, including data management, high performance computing, and he's now an associate division head and leads the scientific computing division's 82 scientists. So it's a big job there. He joined G-2 in 2011, even before the big magnet arrived. So he's been on it since the beginning here at Fermilab. And in recent times, he's been working on quantum computing. So Adam really does a lot of very interesting things in his life. And I look forward to hearing what you have to say tonight, Adam. So welcome, over to you.
Wow, thank you so much, Nigel. I really appreciate that introduction. Let me get things going here. Hopefully you can see me and hear me okay. Let me start my screen share. Yep. Okay, so let me get one more thing. Where to go? There it is. Okay, so great. I'm gonna do one. Hide that. Okay, you should be able to see my screen. So let me start that. Okay, great. Okay, so thank you. Welcome, everyone. It is such a pleasure and honor to be telling you about the first result from our Muon G-2 experiment here at Fermilab, or what can wobbling muons tell us about the particles in our universe. So I'm speaking on behalf of the Muon G-2 collaboration. And let me say first for a second what that means. So the work that I'll be showing is really a work of many, many people. So there are a little over 200 people working on this experiment from 35 institutions and 7 countries from all over the world. You can see on our map, if we want to have a meeting where everyone shows up awake, that's not an easy thing to do. And actually, I should point out, this is a small collaboration. There are collaborations in particle physics experiments that have thousands of people. So we're actually a very small collaboration. And as Nigel said, this is a really exciting time for Muon G-2 in Fermilab. About 2 weeks ago, one of our spokespersons, Chris Pauly, presented the first result from our Muon G-2 experiment. And that's what I'll be talking about tonight. And hopefully some of you got to see that science seminar. So I'll give you some of the background behind this. And as Nigel said, we're just amazed by all the excitement from our little experiment. So I have to start at the beginning and tell you a little bit about what particle physics is and how it works. So the questions we're really trying to answer are, what are the building blocks of matter? What's the universe made out of at the smallest scale, and how do those building blocks interact? What are the forces that go between them? So we start with kind of a standard picture of something like a dewdrop of water that contains water molecules. The water molecules have atoms. Right? And the atoms have electrons and protons and also neutrons. And for a long time, we thought that was the story until in the late 60s, it was discovered that protons and neutrons have internal structure. They actually have quarks inside of them. They have 3 quarks. The proton has 2 ups and a down quark. And we kind of imagine that there's gluons, these particles that carry the strong force that bind these particles together inside the proton and also bind the protons and the neutrons into the nucleus. So now sort of build up the standard model, which is sort of our periodic table of subatomic physics. And I've already told you about three particles, the up quark, the down quark that make protons and neutrons, and the electron. And what's really amazing is that with these three particles, that pretty much describes matter in our everyday world, everything. You, me, the planet, cars, dogs, everything that is made up of up, down, and electrons. There's also, I mentioned the gluons, that's a force particle for the strong force. There's photons, you probably have heard of those. They carry the electromagnetic force. In fact, there's photons hitting from, sent out by your screen, hitting your eyes. So photons are very important. So what's really interesting in particle physics is that as we've done experiments and looked for more particles, we found more. So the electron has some heavier cousins. It has a particle called the muon. We'll talk about this one a lot. And an even heavier cousin called the tau. And then there are other particles that are associated with each of the electron, muon, and tau. Collectively, these are called leptons. And these other particles are the neutrinos. And these are really fascinating, interesting particles. Fermilab has become the world's premier particle physics laboratory in studying neutrinos. We have many neutrino experiments, and we're building new ones. We're building a big experiment in a mine in South Dakota called Dune. You've probably heard talks about that if you pay attention to Fermilab on YouTube and things like that. I won't talk about neutrinos very much. We'll concentrate instead on the muons, but neutrinos are very interesting. And along with the additional leptons, we've discovered additional quarks. So in fact, I was at the D0 experiment when the top quark was discovered in 1995. That was another very exciting time. And so you see there's sort of these three families, three columns of fundamental particles. And then to round out the force carrying particles, we have the photon, the gluon that I talked about, and then there's the weak force, which is involved in radioactive decay. And that has two force carrying particles, a heavy W particle and a heavy Z particle, the W and Z boson. And then there's one more particle that was predicted for quite a while and was finally discovered at experiments on the Large Hadron Collider at CERN. And this particle is the Higgs boson. So this made all the news in 2012, and this completes the picture of the Standard Model. And we think that, well, the Higgs boson is involved in giving mass to particles in the Standard Model. And this is the picture of what we have of the Standard Model. And this has been tested with literally thousands of analyses, and all these particles exist, and we study them. But we have this notion that we want to ask: is this the whole picture? Is there more to the story? And we think that this is not the whole picture. That there must be more to this story. And so we look beyond the Standard Model to try to look for things that the Standard Model doesn't explain, and find other theories that can encompass the Standard Model and explain these things. So, for example, when I went through the forces, you might have noticed that one force was missing. That was gravity. And of course, gravity is very important for us. So the Standard Model does not describe gravity at all. And that's a feature we would like to have. You probably, if you followed a lot of advances in science recently, you probably know that our everyday world is really only 5% of the universe, the matter in our everyday world. We know that there's matter that interacts gravitationally, but not with the electromagnetic force. So, for example, when we look at galaxies and we look at stars at the edges of galaxies, we can calculate by how much mass there is in the galaxy how fast those stars should be going, and we find them to be going much faster than they ought to be going. And we also, astronomers find these structures called gravitational lenses, where there's a background galaxy its picture is distorted by a foreground galaxy, and there's not enough mass in the foreground galaxy to do that. So we think there's extra matter that we can't see, called dark matter. We know the universe has been expanding for quite a while. We know for quite a while the universe has been expanding. And recently, in the year 2000 or so, we just discovered that the expansion is accelerating. So there's some energy that's fueling that, and we don't know what that is. That's called dark energy. We have several experiments at Fermilab looking for dark matter, and then a galaxy survey trying to understand dark energy. So Fermilab is involved in that too. We also want to ask questions like, why is the electron so light and the top quark so heavy? I mentioned the 3 particles that basically make up our everyday world. What are the other particles for? The second and third families, those other columns in that table. We're all made of matter. Antimatter is not really found in our everyday world. Why is that? Where did the antimatter go? And maybe there are more surprises that there are out there. So theorists try to develop extensions to the standard model to try to answer these questions. So pretend you're a theorist and you're coming up with your model to try to explain some of these things. So your model has to have certain things. So for example, you have to, whatever the standard model predicts that we've tested, your model had better do that too. What's right is right, and your model has to predict the same things. Hopefully, your model predicts new and testable phenomena, like maybe new particles that are not in the standard model. So we can build experiments to look for those. Here's an example. This is an extension called supersymmetry that predicts many, many new particles. And we've searched for these at the Tevatron, at Fermilab, and now at the LHC. You can also predict the particles that we know about, but maybe behaving somewhat differently than what the standard model predicts. So those are things we can test. Many of these models have kind of cool sounding names like supersymmetry, supergravity, extra dimensions, things like that to get people interested. So really there's 2 ways that experimentalists go about testing the standard model itself and also looking for these extensions to the standard model. And what we do is we try to make, one way to do that is to try to make these particles in high energy collisions. So the LHC now is trying to do that. And so we'll look for particles we haven't seen before. And also try to look very closely at the particles we do know about, studying them very precisely to try to catch them doing something that maybe the standard model does not predict. And so for that, you need lots and lots of particles. And so we typically call that high intensity. Oh, there we go. Okay, so you haven't heard about any new particles being discovered beyond the standard model, even though the LHC has looked really, really, really hard. All those experiments have many, many analyses looking for particles from supersymmetry and other models. They are still looking. In fact, at the end, we'll sort of talk a little bit about where that's going. So what else can we do while they're doing that? So as I mentioned, we can study some particle properties very precisely compared to the standard model. And this experiment, Muon G-2, is one of those types of experiments that does that. And actually, this experiment is very special. The latest, the one before ours, the result that came from Brookhaven about 20 years ago, Brookhaven National Laboratory, they did this experiment. And they measured a slight discrepancy with the standard model. Not enough to claim a discovery, but enough to be really, really interesting. So we're going to talk about this tonight and what Fermilab has done in our experiment and our result. Okay, so I said I would talk about muons a lot. So muons are, in fact, a really nice laboratory for studying fundamental physics. So here's where the muon is in our table of standard model particles. It was discovered in 1936 by these 2 gentlemen from Caltech. The first one, Carl Anderson, actually got the Nobel Prize for discovering anti-electrons or positrons or antimatter. Basically, they took this device called a cloud chamber up to a really high peak so they could see particles coming down from the sky. They're called cosmic ray particles. And they saw tracks in this cloud chamber, and there was a magnetic field to bend the tracks. And they saw a particle here that didn't bend like the particles that they knew about, not like how electrons and protons bend. And so eventually, this became known as the muon. And muons are like electrons. They're in sort of the same row here in the standard model picture. They have the same charge as an electron. Oh, and the lights just turned off. Can people still see me okay? Or do I need to go turn on the lights again? The lights are on a timer here on this floor, so I'm just going to keep going, and hopefully that's okay.
It might be a good idea to turn the lights on if you can.
Okay, give me 1 second.
Great, thank you.
Okay, sorry about that. I was actually fiddling with the lights, hoping they wouldn't do that, but they did anyway. Okay, so let's see. So muons are like electrons. They're also fundamental. So we think they don't have any internal structure. But muons are unlike electrons in that they're quite a bit heavier than electrons. They're unstable. They don't live very long. They live for about 2 microseconds at rest. Then they decay to electrons and neutrinos. And one thing that's interesting about muons is that they can penetrate a lot of material. So here's a picture of a cosmic ray hitting the atmosphere. It makes lots and lots of particles. Some of those particles eventually are muons. And muons can penetrate buildings and things like that. There's muons going through us right now. They don't really do very much to us. But if you're running a very sensitive experiment and a muon goes through your experiment, that might confuse what you see. So a lot of neutrino experiments that are incredibly sensitive have to go underground to avoid being affected by cosmic ray muons. So this particle that we study very intently is an annoyance for other experiments, which is kind of funny, I think. Okay, so we're going to study a property of the muon very, very closely, and that property is spin. So leptons and quarks have this internal property called spin, and we could say it's an intrinsic angular momentum, and we sort of imagine that it's spinning like a top. We don't know if that's what it's really doing, but this analogy seems to work in many ways. And so if you've all played with gyroscopes, and I hope you have, you spin up this gyroscope, this disc starts spinning really fast, and this thing can kind of stand up all by itself because of its angular momentum. And so we're going to use this analogy a lot, and we're going to say the spin direction is the axis of the gyroscope. So the disc is spinning in a certain direction, and that generates a spin along its axis. So when I say the spin direction, picture this little gyroscope and where this arrow is pointing. We'll see this again. Spin and charge make for a little bar magnet. And when we place a bar magnet into another magnet, then that bar magnet will move a little bit. So if you put, say, a muon in a magnetic field from an external magnet, so here's our muon spinning, and here's our magnetic field with strength B, then the little magnet feels a torque, and the spin will precess. So the spin vector, the axis of this thing, will move around, sort of like it's shown here. And it moves with a frequency that we can measure. And that frequency is related to the strength of the magnetic field, some constants like the charge and the mass of the muon, and this really interesting number here this quantity called G, which is we call the G factor. And the G factor is actually a property of the particle, and that basically says how much that particle interacts with the magnetic field. So if G is really small, then the precession will be really slow, and you can say, well, the particle is not really feeling the magnetic field. If G is really big, and so then the precession frequency will be really fast, then the particle is really feeling that magnetic field, right? So this sort of measures the strength of how well a particle feels a magnetic field. So if we can measure some of these things, we can measure the precession frequency, and physicists can measure frequencies really well. And if we know the strength of the magnetic field, whether it's a refrigerator magnet or an MRI magnet, we can measure that or determine that. Then we can measure what this G factor is. And that's in fact what we've done. So the G factor is really important. It's a quantum mechanical effect, and quantum mechanics actually predicts that G is equal to 2 for a point-like particle. And this was actually derived by Paul Dirac, a very famous physicist in 1928. And this was confirmed with electrons in the 20s and 30s, that G was about equal to 2. Interestingly, a little bit later, when people measured G for the proton, it wasn't. They didn't get 2. They got kind of a strange number. And that was one of the first indications that protons and neutrons too have an internal structure, that they're made of quarks. They're not point-like particles. This, of course, was figured out much later, but this was kind of a hint of that. And then in the late 40s, as there was a surprise, this G factor for the electron, which had been close to 2 for quite a while, Foley and Kitch did an experiment where they found G to be a little bit greater than 2. Not much greater, but a little bit greater. And their uncertainties could not account for this discrepancy. Their uncertainties were quite good. So this plus or minus 0.0010, that's how their degree of how much they believe this number is right. So it's so the 3 could be a 2 or a 4. And actually, the way this is written is kind of a pain. All these zeros. So what we actually like to do is say the last 2 digits, here's the error in the last 2 digits. That's the same as what you saw before. So, what's going on here? So G for the electron is now measured to be a little bit greater than 2. Why is that? Does the electron have some internal structure? And the answer is, in fact, no. So here again is the result. G is a little bit greater than 2. And actually, the 2 is kind of a pain. So physicists like to get rid of things that are a pain. And so we actually have a new quantity called the anomalous factor. And for that, we actually subtract off the 2 and divide it by 2. So it's the fractional part over 2. And this is what we call the anomalous part of the magnetic moment. And so basically all you have to remember is if A is greater than 0, then G is greater than 2. And we'll kind of go back and forth. And I have these in green to sort of say that these are all related. So what's going on here is that if you study quantum mechanics actually says that, and this is the theory that describes how subatomic particles work and their world. Quantum mechanics says that empty space is not actually empty, and that any particle can quickly and randomly appear and disappear by quickly borrowing its energy. This is related to the Heisenberg uncertainty principle. And so let's just have a little animation here. So say you have a muon spinning around and a photon appears. This could be a muon or an electron. It doesn't matter. They do the same. Or you have a photon appear, and that then goes into an electron-positron pair, and then you get a photon again. Or maybe 2 particles with quarks appear, or Z boson appears, or interestingly, maybe something we don't know is appearing and disappearing. And so these are called virtual particles. And actually, we can see them inside, see their effects inside protons and neutrons and things like that. So we know this picture actually works. And so if G being a little bit more than 2 accounts for these effects from all these virtual particles. And you can actually, so remember here we have this result a little bit more than 2. And this a little bit more than 2 was first predicted by this gentleman, Julian Schwinger, who got the Nobel Prize for this. This was in, I guess, the late 40s, early 50s. So the way this works is that we imagine sort of the G factor being built up by the basic thing that's happening, the 2 part, which is the electron interacting with the magnetic field. That's this photon and the X. That's the magnetic field. The electron sort of says hi to the magnetic field and then goes on again, so in and out. And then this little extra part here is where the photon sort of appears. And so the electron gives a little energy to this photon and gets it back later on. And Schwinger actually calculated how much this interaction adds to G. And so he got this, which very closely matches what Foley and Kutch got. So this is the start of what we call quantum corrections to these diagrams. Actually, the same thing happens for the muon. This was confirmed in the 50s and 60s. And actually, Leon Lederman, who was the second director of Fermilab, he led one of these experiments in the 50s for G-2 of the muon. Okay, so I showed you that one picture of a quantum correction. Here that is, involving the photon. You can have other pictures as well. You can have the Z boson, that one I mentioned. You can have photons that go to quarks, that go back to photons again. And then you can have very, very complicated, funny-looking diagrams like this one, again involving quarks. That's sort of the blue ball there. And you can sort of go wild. There's really an infinite number of diagrams involving, lots and lots of these little loops. You can imagine, 2 loops, 3 loops, 100 loops, and really interesting-looking things. You can make them look like Space Invaders if you want. It's kind of neat. But there is a fortunate rule. There's a good thing that happens. Even though there's an infinite number of diagrams, the more complicated the diagram, the less it contributes to the G factor. So the more stuff going on, the less it contributes. And so this one, the most basic one, that's the one that contributes the most, and the more complicated ones contribute less. So at some point, you don't have to calculate anymore because it just doesn't, they don't add very much. However, as our experiment precision improves, then you have to start worrying about some of these more complicated diagrams, because these sensitive experiments, can see their effects. And so to account for the precision that our experiments are at now, the theorists have to calculate over 13,000 of these diagrams to calculate what the standard model prediction is for the G factor. And some of these are very difficult to calculate. And there's sort of an industry behind doing this. In fact, the theorists themselves have their own collaboration now. This is only a couple years old. There have been a lot of groups, theory groups, calculating parts of G-2. And so they formed their own collaboration to come to a consensus, to put together all their different ways of doing things, and come with one number for the standard model prediction that they can all agree on. And this is what now the Fermilab experiment, our experiment, we will compare to their value. So we no longer choose which theorist to follow. The theorists themselves get together and give us the best value that they think is right. Okay, so I showed you also in that animation that there could be question marks. There could be particles that we don't know about that are in the mix of retro particles and could be affecting the G factor. And that's what's really exciting, right? That we could be sensitive to particles that are not in the standard model. And then we can ask the question, is the standard model complete? So here's the game plan. So the theorists will calculate G, the G factor, or A, the anomalous part, with all these diagrams from all these corrections from the particles that we know about that the standard model has. And that's the standard model prediction. Experimentalists, like myself, make an experiment and measure the anomalous part of the G factor with great precision, right? Precision that matches their calculation. And then we look to see, do we agree? Is there a discrepancy? And if there is a discrepancy, well, then that's really interesting. Maybe there's a hint that there's something else going on outside the standard model that's affecting our muons. And if we agree, well, that's also, that's interesting too. Maybe you would agree not quite as interesting as finding something new, but that's okay. It's all interesting. All right, so how do we actually do this experiment? So we need a couple of things. First of all, we need muons. We need something that gives us muons, a source of muons. Using muons from the sky, from cosmic rays, there are not enough of them in any one place to really use them for this sort of experiment. Although there are other experiments that study those cosmic rays, but we need a lot more muons than that. We need a magnetic field to make the muon spin process, right? I showed you that gyroscope that's processing. And we need to put them somewhere where we can watch them for a while, right? We have to give time for that precession to happen and time for the muon to decay. And so we have to actually watch them. So there's a device called a storage ring, and that's what this picture is here. This is the storage ring of Brookhaven. This was the experiment done 20 years ago. And storage rings are really nice for this sort of thing because it checks off two of these boxes. A storage ring keeps the muons going in a circle. That's what the magnet, this is a magnetic storage ring, so what the magnet does. Keeps the muons going in a circle, so we can keep them there for a while. And it provides the magnetic field to make the spins process. And so this was the ring of Brookhaven, and that's what we're going to use. Actually, Brookhaven has this really, really nice diagram here to show how the experiments work. So I'll use it too, and the Fermilab experiment is almost the same. So you have a source of protons. Brookhaven has their accelerator. We have our accelerator complex that takes protons. We always start with protons because that comes from a hydrogen bottle, and then those go through our accelerators, and we accelerate them to high energy, and then we smash those protons into a target. And because energy and mass are interchangeable, that's E equals mc squared, a lot of the energy that those protons are carrying because they're going very fast can be converted to new matter, and we can make a lot of different types of particles. A lot of stuff comes out, but particles called pions are the ones we're interested in. They're made of two quarks, and those pions will decay to muons and neutrinos, and these muons will have a very special property. So let's look at that for a second. So here's here's protons hitting a target. We got lots of stuff. Some of what comes out are pions, and a pion will decay after a short period of time to a muon and a neutrino. We actually use pi pluses because protons are positively charged, and they like to make pi pluses, and so we're actually going to use mu pluses or anti-muon. So actually our experiment uses antimatter, which is kind of cool. So the pi pluses decay to muons and a neutrino. And actually we use this to also make neutrinos. We don't care about the neutrinos. You need a very different beam if you're going to study neutrinos. So we make the muons and the neutrinos just go on their merry way, and we never see them. they can go through everything, so it doesn't matter. And what's a neat thing is, remember how the spin works, that we have the spin axis. When the muons are produced, their spin is always in the opposite direction that the muon is traveling. That is a property of the weak force, which is how this thing decays, and we get this for free. This is physics. So the muon spin is always in the opposite direction of the direction the muon is going, and so we can make a beam where all the muon spins are all pointing the same way. And this is called a polarized beam. And this is really key. If we had randomized spins directions, that wouldn't work. We need all the spins pointing in the same direction. And we get that. In fact, it's hard not to get that with pions. Okay, so the muons go into the storage ring, so here, and they go around, and their spins precess as they go around the storage ring. So let's look at that. So remember, here's our little formula for relating the spin precession frequency, how fast the spin is precessing around, how many times around a second. It's related to the G factor and the magnetic field. This is when a muon is at rest, but our muons are moving. They're going around the storage ring. Here's sort of a top-down view of the storage ring, our little racetrack. And this formula is a lot more complicated. I won't scare you with it. But there's a really neat thing that does happen, that if you take this formula for the spin frequency and subtract off what we call the cyclotron frequency, then we get this frequency called omega A, which is directly related to the anomalous part of the G factor. So all we need is to measure to know the magnetic field really well, some constants, and this frequency, and then we can measure what this anomalous part of the G factor is, or how much of it is greater than 2. And so what this cyclotron frequency is just the rate at which the muons go around the ring. And so we imagine this has a vector called the momentum, and this momentum vector spins just in the direction that the muon's going around. So it just goes around in a circle. And so if you just look at the vector itself, this is what it's doing. Oh, I was meant to fix that. So it just goes around, and it's just pointing in the direction of the muon. That's all that it does. So nothing interesting there. So let's play some games. So if G is exactly equal to 2, that means that A is 0, right? And the spin precession frequency is the cyclotron frequency. And if that were the case, then I'll show you here, then the spin vector, which is in red, is in lockstep with the momentum vector. So as the muon goes around the ring and its direction points in a different direction, as it goes around, the spin direction follows that in lockstep. Okay, so now let's say G is a little greater than 2, which of course we know that it is. So that means that A mu is a little bit more than 0. And so that means that the spin precession frequency is a little bit greater than the cyclotron frequency. And so that means the spin vector will advance a little faster. And that's what's shown here. Notice that the spin is now getting out of sync with the direction. I don't rotate the middle ones because that'll make you nauseous. And you can see sometimes it's forward, sometimes it's backwards, and in between. And so actually, I exaggerated here. For the value of G minus 2 for the muon, it takes 29 times around the ring for the spin vector to go all the way around once. Let's try to hit this home a little bit more. I'm going to get 2 friends to help us. These are our 2 doggies, Riley and Rini. We adopted them about 7 months ago. And so if G is equal to 0, actually, we're going to do this. We're going to rename them spin and momentum just for this talk. And so if G is equal to 0, spin and momentum should rotate around the same rate. And hey, they did. And if G is a little greater than 2, spin should go a little faster. Okay, we're still working on it. Hopefully, maybe by the next result from G minus 2, we'll have all that figured out. So anyway, so these muons are the spin is precessing. If G is greater than 2, it's precessing at a faster rate than the muons are going around the ring. And then the muons decay. The muons, we have positive muons, so they decay to positrons or positively charged electrons. And then we can catch those electrons in a detector called a calorimeter, those positrons, in a calorimeter and measure their energy. So let's see how that works. And there's another really neat thing that happens because of the weak force. So imagine, I'll first start out with muons at rest. And so muons will decay to a positron and more neutrinos. Lots of neutrinos are being produced here that we don't care about. They just go on their merry way, and we never see them. We care about the positron. And the really neat thing is that the way the weak force works is that the positron, when it is emitted from the muon, the highest energy positrons are emitted along the direction of the muon spin. So here is our little gyroscope. Here's the direction that the spin is pointing. If this muon were to decay to a positron, the positron will come out in the direction of that spin. So here's another one, comes out in the direction of that spin. One more, comes out in the direction of that spin, right? So that's really neat. That means that this positron is carrying information about the spin of the original muon, right? So by looking at these positrons, we can get information about the spin of the muon that it came from, right? So we can actually see this then precession of the muon spin through these positrons. So I hope that made sense. We're going to actually go a little bit further because that was for a muon at rest, and our muons on the storage ring are moving, and they're moving fast. They're going, almost the speed of light. And so what happens then is that basically the direction that the positron is emitted is always along the same direction as the muon. The muon is going so fast that basically it's like throwing a ball from a fast-moving train, right? If you're on top of a train and you throw a ball, that ball is going the speed of the train because the speed of the train is overwhelms however fast you throw the ball. But the ball, or in this case the positron, will get a little boost of energy, either a boost or kind of an anti-boost, depending on if it's thrown off along the direction of the muon or in a different direction. So we have these detectors called calorimeters, which I represent as a catcher's mitt. So the catcher's mitt will catch the positron, and it'll measure how much energy that positron has by sort of how hard it hits that catcher's mitt. So if the spin is pointing in the same direction as the muon momentum, so the spin is pointing along the direction the muon is traveling in, that positron will hit the calorimeter, and the calorimeter will register really high energy. That positron is getting a boost from the muon's motion and muon's direction. If the positron is emitted in the backwards direction, so backwards from the direction the muon is traveling in, it'll get a boost too, because the muon is still moving from left to right, but it'll get a little bit less of a boost. And so the energy that is registered by the calorimeter will be a little bit less than what it was if it's in the forward direction. And if it's in between, still the positron always comes out, in the direction of the muon because it's overwhelmed by that. But the energy that the calorimeter registers will be in between the lowest and the highest. So from this, you can sort of see this picture of how we can maybe use these calorimeters to measure the positron energy to get information about where that muon spin vector was when it decayed. And so the way this actually works here's a piece of our storage ring. This dashed line here is where the muons actually go. So they're going around the ring. The muons will decay to a positron. The positrons actually are lighter and a little slower than the muons, so they curl inward out of out of where they should be in the magnetic storage ring, because the storage ring is not set up for positrons, it's set up for muons. So it'll curl inward, and it'll eventually hit our catcher's mitts or our calorimeters. And sometimes it can go really far into the catcher's mitt, and sometimes it don't go very far at all. And that depends on kind of where the spin vector was when the muon decayed. So in a more complicated picture, I showed you sort of one positron at a time. It's actually not what we get. We get lots of positrons, and they all have an energy distribution. So this sort of shows what the energy distribution is. And here I show a threshold energy where we're going to look at how many positrons come in above this energy. And so when the spin and the spin vector and the momentum are aligned, then this spectrum is pushed really high because the positrons get a nice boost. And I'm going to see if I can control this here a little bit. And so as the spin vector turns around, so here I'm going to stop it and go, oops, I did that. There we go. Oh, there we go. So when it's backwards, notice that the energy spectrum is lower above the threshold and it's pushed to the left, and it gets higher and higher and higher. And when it's aligned, it's the highest. Looking at the left picture here, and then when it's anti-aligned, it's the lowest. And so this oscillates, right? So now on the right-hand picture, I'm going to go back to the beginning and stop it. On the right-hand picture, we're now counting these positrons over this threshold energy, and I'm going to plot how many of these we see. And so when the spin and the momentum are aligned, we see a lot. That's like 30. It's really high in the upper right inset plot. And then as it gets anti-aligned, it gets low, and then it gets higher again. as it comes aligned, and then lower when it gets anti-aligned, and then higher again when it's aligned. So hopefully that makes sense. Let's let this run. And so we build up what's called the wiggle plot. As these muons are going around the ring, their spins are precessing, they're shooting out positrons, and that positron energy depends on where the spin vector is. And we can tell where that is by basically measuring how many positrons we see over this threshold, and we see this oscillation. And remember, this oscillation, the frequency of this oscillation is omega A, and that's directly related to the anomalous part of the G factor. So we can measure G-2 by looking at the frequency of these oscillations. And that's basically how this experiment works. Okay, so if that wasn't clear, I can talk about it more at the end. And you can ask me questions about it. So Brookhaven did this experiment and collected billions of positrons and made their wiggle plot. I'll show the one from Fermilab a little bit later. And so they came up with a result for the anomalous part of the G factor, and it's lots of digits here with the error in the last two digits, which is really, really far out. Compare that to the Cuchin-Foley number from 1948, and to see how much more precision we have compared to what they had. We have the standard model value, and then we can compare. We take the difference. And that makes this gap here. Here is where the Brookhaven result is with their error bar. That's the error here. And we call this a 540 parts per billion measurement. That's the precision. And I'll talk about that in a second. And that makes for this gap. And we can characterize the significance of this gap in standard deviations, or sigma, and it's 3.7 sigma. If the error bars were smaller, if this error were improved, then this would get better. This would get larger. And so that's what actually Fermilab was going to try to do. But this is 3.7. The gold standard for a discovery is 5 sigma. And so so it doesn't quite meet the level of a discovery, but certainly very, very interesting. And actually, just to give you a sort of hint of what a part per billion is, you know what a percent is. That's a part out of 100, and a part per billion is a part out of a billion. So basically, the way we calculate it is very simple. You take the uncertainty, which is in these last two digits. You divide that by the measured value, and that's the result. And you multiply it by a billion, and you get the parts per billion. So how precise is this? So if you pick a nice round number, like 100 parts per billion, that's equivalent to measuring the length of a football field to about 10 microns, or less than the width of a human hair. So that's really, really, really very precise. So that gives you some picture of the precision of these experiments. Okay, so Brookhaven got their result. They got a 3.7 sigma discrepancy. So not a discovery, but also very interesting. And actually, this has generated an enormous amount of interest. This plot shows the number of citations to the papers from Brookhaven over the years, and that really has been sustained for a long time. But for Brookhaven to make big improvements to this would have been very difficult. And so Brookhaven does a lot of other things. And so they stopped working on G-2, and the ring sat for quite a long time at Brookhaven. And then around 10 years ago or so, a little more, at Fermilab, some people started to get the idea that, this is so interesting that maybe Fermilab should do the experiment with a lot of improvements to first check to see if the Brookhaven result was right. Would we get the same result too, or would we get something different? And aim for this 5 sigma discovery level. So if we do see the same deviation that Brookhaven did, by the time we would be done, we would have an undeniable signal of new physics if in fact that really happens. So the goal is to really do this experiment here again at Fermilab with a factor of 4 in better precision. And that involves delivering 20 times the muons that Brookhaven saw here at Fermilab. So we need 20 times more muons. We have a very powerful accelerator complex that can actually do that, and also make many improvements to basically do the experiment 3 times better in terms of what uncertainties of how well we do things, and things that maybe we have to be very careful about. Do those things 3 times better to really improve this error, this uncertainty. And also to try to reduce our costs by reusing the big parts and expensive parts of the experiment from Brookhaven, and also other components that were freed up when the Tevatron collider shut down at Fermilab in 2011. So we've actually recycled a lot of stuff from the Tevatron. Okay, so moving the ring from Brookhaven to Fermilab, that was an amazing thing. So first of all, the ring is made up of coils. So here's 2 coils here, top and bottom, and then there's a coil in the back. Those are continuously wound wires of niobium wire that they're superconducting, so that makes the magnetic field. And they go all the way around, and we can't break them. If we break them, we got to make a new magnet, and that's really expensive. We also can't flex these things more than about 3 millimeters. And these rings themselves are big. They're 50 feet in diameter. So if you stick that on a highway, that takes about 4 lanes of a highway. So they're not easy to drive around. Fortunately, there's nothing hazardous about them. So in that sense, it's easy, but they're big and they're very fragile. So we contracted with a company called Emert to move the ring from Brookhaven to Fermilab. And so they built this gigantic frame that the coils sit in. You can kind of barely see them here. The next slide will be better. To really rigidly hold these coils so that they would be very, very, very protected. And then we put the ring on a barge. We slid it out of the building at Brookhaven, put it on a barge, and basically drove it on the barge down the eastern seaboard around Florida, up the Gulf of Mexico to Mobile, Alabama, where the Tennessee Tom Bigby waterway, where that entrance is, and then up there, eventually hit the Mississippi, and then on to Illinois. And so this was an amazing, water journey for 3,000 miles. It took 3 months. We got some really neat pictures. Here's where the ring is being handed off from the ocean tug to the river tug. And here it is going by the St. Louis Arch. And then here it is arriving in Lamont, which is about 30 miles from Fermilab, which is the closest point on the Illinois River where the magnet could be offloaded from the barge. So then the magnet was still 30 miles away from the lab down here in Lamont. And so we had to drive it across the Chicago tollways, the highways in the suburbs, from Lamont to Fermilab. We did that over 3 nights. So here it is actually on Interstate 88 with all of its support traffic. I was very lucky. I was in a car following the ring. It was really, really cool. And then behind us, the traffic was stopped. I'm sure they were not very happy, but all in the name of science. And actually during the day, in between these moves, the magnet would sit. And so it actually sat across the street from a Costco, and a bunch of us brought some brochures and talked to lots of people. It was really neat. And then it arrived at the lab, and we had a big celebration. We opened the lab so that people could see it. And actually, we had no idea how many people we would get. And it turns out thousands of people came. In fact, so many people came that we had to eventually start turning people away. We ran out of parking. So it was an amazing thing. And here's my family in a photo op in front of the ring. A lot of people did. So eventually we built our building that the ring goes into, and we call this area the Muon campus. So this will support our experiment, G-2, and another experiment that's under construction called MUDE. And this part down here is part of the delivery ring where we deliver muons to this campus. And that's actually recycled from the Tevatron. This is the old Tevatron antiproton source. And here's our 2 buildings. And so here's just a couple slides putting the ring back together. So we have this base of iron. This comes in pieces, and so we truck that from Brookhaven. Here's the ring itself now sitting on top of it. We can slide it into the building. The front of the building comes off, and we slide it in, and then we lower it onto this platform. And then we build up more iron that also got shipped by truck from Brookhaven, and this actually forms the magnetic field. Here are the 2 inner coils, and the muons kind of go in this inset region in between the 2 coils. So that's what that looks like. I talked briefly about how muons are created. So we do something sort of similar to what Brookhaven does. We have rings and accelerators that accelerate protons. They're very high energy. So protons from our accelerator complex eventually make it into this ring called the recycler ring that kind of reorganizes the bunches of protons and sends them to a target station. So that's our big block of metal. We have a cylinder of nickel alloy that the protons hit. About 1 trillion protons at a time hit this target, and there are 16 bunches of protons in about 1.4 seconds. So each bunch has about 1 trillion protons. They hit this target, a whole lot of other stuff comes out the other side, as I mentioned before, including pions. And these pions, remember, they decay the muons. There's a beam line here where these pions will decay. Remember, all these muon spins are pointing in the same direction. It's a polarized beam. So that's what makes this experiment work. And eventually these muons go around this delivery ring. That was sort of those 3 bunker buildings that I showed you before. And they go around this ring a couple times, 4 times typically. And that's because there are other particles that are coming along with the muons, and we don't want those particles. We don't want them hitting our ring because they'll make a mess. And so actually we use this delivery ring to separate out those particles from the muons, and then we throw those particles away and let the muons continue on into our ring. So out of 1 trillion protons that strike the target, about 250,000 muons make it to this point down here right before they enter the building for the G-2 ring. And so here is the G-2 ring. It's the same Brookhaven ring. The magnet itself is the same, but everything else is new inside this magnet. Although some things are recycled, these beamline components here, these magnets, this is where the beam comes in. The muons come in this way from the building, outside the building, into here. They go into the G-2 ring. These magnets are recycled from other parts of the lab. So about 250,000 muons enter the ring. There's sort of a tortuous route they have to follow to get stored, to continue going around. Only about 2% make it through that. So we actually only store about 5,000 muons at a time. These muons are going really, really fast, 0.9994 the speed of, times the speed of light. And so if you remember special relativity, when you have something going really fast, its clock to us looks like it's going slower. And so a muon that would at rest live for 2.2 seconds, on average, lives 64 microseconds. Sorry, 2.2 microseconds, lives 64 microseconds. And this is great because the muons will live quite a long time. They'll go around lots of times. Actually, this is the average. So some muons live shorter, some muons live a lot longer. And so we actually allow these muons to go around for 10 muon lifetimes. So after about 700 microseconds, they're all gone. They've all decayed. And we fill the ring 16 times every 1.4 seconds. And the ring is at a very high vacuum, so the muons don't hit anything. The magnet itself is superconducting, as I mentioned. We have to put high current in this magnet to get the magnetic field we want. And so we have liquid helium going around those coils at 5 degrees Kelvin or negative 450 degrees Fahrenheit. The magnet strength itself is about the same as a standard MRI magnet in a medical office. So pretty strong, not super strong, but strong, but quite strong. And we've done a lot of work. It took us a year of adding little bits and pieces, little bits of metal here and there, and turning knobs to make the magnetic field itself as uniform as we could all the way around the ring. That really helps us with the analysis. And then we had to measure the magnetic field. Remember, there's the B part of our formula. We have to know what the magnetic field is. And so we measure that. We have embedded probes, hundreds of embedded probes inside the ring itself. And then we actually have a little trolley, it's a little railroad car that goes around the ring, the little rails here. And the trolley itself has 17 probes on it, and it measures the magnetic field as it goes around in 9,000 stations as it goes around the ring. We can't have muons in the ring while the trolley is going around, because the trolley will block them all. But that's okay. So, and we take a break every 3 days running muons, and we stop the muons, and then we run the trolley and measure the magnetic field. So that's really kind of neat. So again, back to the muons enter from the back. They have to enter this magnet. So there's actually a hole in the coil where the muons can enter. And this actually is a neat picture looking down these magnets here. But the muons go into the ring. There's actually a special magnet called the inflector that cancels out the magnetic field of the ring where the muons are entering, because the muons wouldn't like seeing a very big magnetic field all of a sudden. And so we have to cancel the magnetic field with this strange looking magnet. And when we do that, unfortunately, there's a problem in that the muons don't quite enter at the right orbit. So if we didn't do anything, if we just let them keep going, they would all kind of hit the wall here and we would lose them all. So we actually have to kick the muons onto the right orbit. And so as the muons are going around their first time around the ring, when they hit about a quarter of the way around, there are these plates that we charge up to very, very high voltage, and they fire within about 100 nanoseconds. So 100 billionths of a second. And as the muons are going by, they are kicked about 10 milliradians, so not very much, but just enough so that they will keep going around the ring. And so we won't lose them. So these kickers are very important. And actually, these kickers, we need them, they're essential, but they also cause us a little bit of headaches, which maybe I'll get to and explain that. There's another complication in that the magnetic field itself of the ring keeps the muons focused, but only in kind of the horizontal direction. So here's kind of a cross section of what the beam looks like, the vacuum region. So the muons are in this region here. They're going into the screen at some level. So imagine the muons going by into the screen, and so they live in this circle here. It's a 9 centimeter diameter spot where the muons go, and so they are focused in the horizontal direction. So they'll stay in the ring. But if we didn't do anything, they're unfocused in the vertical direction. So they would basically get more diffuse. They get taller and taller. The beam would get more and more spread out vertically, and eventually we would just lose them all after a couple of turns. So we have electrostatic plates, these quadrupole plates, that act as a lens. There's 4 of them here, one on each side, and we charge these up, and these keep the beam vertically focused. So that's really important. If we didn't do that, we would lose the beam. So we need these things to keep the muons in the ring. And then we have the detectors, the calorimeters, the catcher's mitts, right? So we have 24 of these things. I pointed out a few of them. And so these are little boxes that are inset sort of into the ring where the positrons go. Remember, the positrons curl inward. So we have these boxes to catch them. And they sort of at the end of these carts to have all the services for these calorimeters. And there's, like I said, 24 of them all the way around. And these calorimeters are actually lead fluoride crystals. So when a positron enters a crystal, it kind of rattles around inside the crystal and makes lots of other particles and things. And the crystal reacts by giving off a tiny, tiny bit of light. It gives off photons. And we can capture those photons and measure how many photons there are with a device at the end called a SIPM. And basically, the more light that gets produced, the more energy the positron has, and the more signal we'll see on these SIPMs. So that's how we do that energy measurement. That's how we measure that spectrum, the oscillating spectrum. That's what these calorimeters what they do, these catcher's mitts. Okay, and then we also have devices called trackers, these weird straw-looking things. So actually inside these straws, these are where the positrons go. So the positrons go through these straws. They're very thin, so they don't really block the positrons. Inside these straws, there's a wire and there's a gas. And when the positron goes through the straw, it ionizes the gas, and the wire senses that. And so it's a little hard to see. Here's sort of where these trackers are. If you look carefully, these little black dots where the positrons hit the wire. And so we can sort of connect the dots and extrapolate back somewhere around here and see where the muon was when it decayed. So we can get a picture we can deduce where that muon was when it decayed to the positron. And that's a really important thing we need to do. Just very quickly, I'll show you a little movie. I got to turn off the laser pointer. If you were a muon, this is kind of what you would see. It's not stop and starting. This is on a trolley. Here's the trackers. The trolley has to move along. There's the calorimeters behind here, and here are the quadrupole plates. So of course you're going around. It takes about 140 nanoseconds, 140 billionths of a second for a muon to go around the ring. So you'd be going around a lot faster. All right, I'm getting close to the end. So let me just go through this sort of briefly. So I mentioned the kicker causes some complications. And so the beam itself, you imagine where the beam of muons are in the ring, they kind of slosh around. And so we say the muon beam swims back and forth. This is sort of as what the muon beam looks like as it's going around the ring. So it kind of, in this box, this 9 centimeter diameter box or circle, the muons kind of slosh around. So it swims, and the width of this gets bigger and smaller. And so we say it swims and it breathes. So the muons are not always, in the center, which causes some problems. But we have to figure that out and deal with that. We have other interesting things like we have 2 low energy positrons from decays that enter the calorimeter at the same time, or a calorimeter at the same time. The calorimeter might not be able to tell them apart if they're so close in time. So it'll actually add the 2 together, and it'll look like a really high energy positron from a muon out here. So this is called pile up, and we have to actually figure this out and subtract that off. Because that's actually a mistake. It's an unavoidable mistake, so we can figure that out by different means, simulation and from data, and we can subtract that off. We can have muons on the edge of the beam that hits things, and then curl inward, and maybe hit a colorimeter. So muons doing that would confuse us a little bit. We can actually figure that out by looking at data and figure out how often that happens. The temperature in the Hall, this was our first run, so we were learning things for the first time. The temperature of the Hall was not well controlled, and so that changed the magnetic field of the magnet a little bit. So we had to deal with that. These kicker plates are very high voltage, and so sometimes we would get sparks. So we had to actually run the lower voltage than we wanted. And we also, the quadrupoles have high voltage resistors, and the company that made them for us couldn't quite make enough of them. So we tried to make a few of them ourselves, and we didn't make very many. Like, I think we made like 4 or 5 of them, but 2 of them didn't work so well, and so that created some problems. But anyway, we have to figure all that out. That's part of what we do. And so here is our wiggle plot. So remember, I showed you the building up the wiggle plot, and so this is what ours looks like from our experiment. It looks sort of like what you saw there, building it up. And so one thing to note, this wiggle plot wraps around. So if I showed you, the one long, thin wiggle plot, that'd be really hard to see. So this point here wraps around to this point here. So overall, it's about 700 microseconds. It's actually, you can see it's kind of sloped downward. And that's because we're actually measuring the number of positrons. And as muons decay over time, there's fewer and fewer positrons because there's fewer and fewer muons for them to come from. And so so you're seeing the number of muons decrease over time. And this is the result of 18 million fills, 18 million fresh batches of muons, and 8.2 billion positrons total, which is a little more than what Brookhaven saw. And this was a little more than a month of running. So what took Brookhaven about 3 years to do in terms of data, we can produce about the same amount of data in a little more than a month. Right, and so this is, shows the power of the Fermilab complex, that we can make a lot more muons. One thing to note is that I have weird units here. I said this was 700 microseconds, so this point here should be about 102.5 microseconds, but it's not. It's about that, but we don't actually know what this point is, and that's because we've blinded this experiment. We've actually shifted the time here by a secret amount. We don't know on the experiment. We didn't know what this was. So we could extract omega A. We could figure out what this frequency is, which would be omega A, which would lead to the anomalous part of the G factor, which is what we want. But we would actually get an answer shifted by a secret amount. So we couldn't actually figure out the answer. We could do everything else, but we couldn't actually know the answer. And that was something really important for us to do, because there's sort of an answer that everyone's hoping for, right? We're all hoping that maybe we'll confirm the Brookhaven experiment. And when you have something you're hoping for, and you sort of know how things are going, you can unconsciously make decisions that kind of reinforce the result you want, right? And we don't want to do that, right? We're scientists. We have to keep our cool. We don't want to be tempted into sort of driving the result into something that we want. And so we actually make it so we can't figure out the result until the very end. So we have no idea, are we matching the standard model? Or are we confirming Brookhaven? We have no idea until we're done. And so there's a secret blinding factor. We actually detune one of the clocks that feeds into the experiment, which changes what omega A we would get. That secret value is kept in 2 sealed envelopes, one at Fermilab and one at Seattle, where we have a lot of people who work on the experiment, and it's in 2 places for safekeeping. And as I mentioned, we blind the results to prevent biases from human nature. And so we don't unblind until all the analyses are done. And we have a rule that once we do unblind, we're not allowed to change anything. What we get is what we get. And so we make public whatever answer we get. And that is a rule that we have to follow. It's actually in our bylaws for our collaboration. And so I won't spend too much time on this. Don't worry about the numbers. This just shows a lot of the uncertainties and corrections we figured out. But this was an enormous amount of work. It took us 3 years after collecting the data to do all the analyses. We had 11 groups doing the analyses, each with a different technique. They all had to agree in the end. And we had many, many checks, and we solved many problems and estimated uncertainties for many problems. We had checks and cross checks. So it took us 3 years to do all this. And once all this was done and we all checked each other's work and saw presentations about how all this was done, then we could consider unblinding. Remember, once we unblind, we're not allowed to change anything. So whatever it is, it is. So whatever mistakes we made, we better figure this out before we unblind. So about in February 25th, a little more than a month ago, we all got together. So we had about 170 people that was the authors of the Run 1 paper, which is a fraction of our data. We all got together and we all had to vote. And the vote had to be unanimous in favor of unblinding to proceed. And if we didn't vote unanimously, then we wouldn't unblind. We'd have to look harder and maybe understand, what was the concern from that particular person. That wasn't the case. We were satisfied that we've done everything we could, and so we voted unanimously to unblind. So before I show you the answer, you probably already know the answer, but let's look to see what we could have gotten. So very quickly, so here's sort of the answer plot. Here's what Brookhaven got with their uncertainty bars, and here's where the standard model is, right? And here's this gap, this 3.7 sigma gap. So what could Fermilab get? Well, we could get a result that confirms Brookhaven. If our result overlaps the Brookhaven result, then essentially we're confirming Brookhaven, and we also would have a discrepancy with the standard model. And as I said, this is sort of what we're kind of all hoping for, right? That would be the best thing. Although we got to keep our cool. That might not be what we get. And of course, we blinded, so we're not influenced by this. We don't make decisions based on that. We could confirm the standard model, right? That would be interesting. That would beg the question as to why the Brookhaven result is so different. Maybe they just got unlucky and saw what we call a statistical fluctuation, but that would have to be investigated. So this would have to be explained why we got the standard model value and they didn't. That's a possibility. We could get something in between. So that's sort of the most unsatisfying answer because we can't really say what's going on here if we get something in between. We would have to analyze more data, which is what we're doing, and hope that this will either move around. Maybe we're seeing a fluctuation, or maybe this is the right answer, and then our error bars would get smaller in the same position. So we would have to look at more data before we could really say anything. And then there's sort of the nightmare scenario where we put in our calculations, we get the point on the plot, and it doesn't show up on the plot. It goes somewhere else, right? Something weird's going on. We were pretty sure this wasn't going to happen. We had done so many checks and so many cross checks, and we were confident. We would not have unblinded. We wouldn't have decided to unblind if we thought there was something that we missed. So we really were confident that we wouldn't get some weird answer. But you don't know until you look. Right, and once we've unblinded, whatever it is, that we have to make public. Right, so I'll just go through this quickly.
Put it in the chat.
Getting a little late here. So we open up the envelopes. Here's Dave Herzog from the University of Washington, opening up his envelope with the secret factor. It's the bottom number. There are actually two clocks that we blinded for various reasons, so it's the bottom number that matters. Here's Chris Pauly, our spokesperson at Fermilab. He opens his envelope, gets the same answer, the same number, so that's good. So we have the same secret unblinding number that we put into our notebook, and we get the answer. So here I'll let this play so you can hear what our reaction was. This is pretty cool.
And this is what we get.
Whoa!
Wow!
Oh,
Wow! Oh my God.
we confirm age 21.
So we confirm the Brookhaven result. Here's our result here. So you have to realize for us, this is like landing on Mars, right? I mean, this is the Mars lander successfully reaching the surface of Mars. This is our Mars lander moment. And so we did, in fact, get a result very close to the Brookhaven result. Here's the numbers. I won't go through the numbers, of course, lots of numbers. But basically on the graph, here is our Fermilab result. And yes, we're a little bit to the left of Brookhaven, but we substantially overlap. And so we confirm their result. And again, this is why we unblinded, right? Because if we did this while knowing the answer, we would have to prove to people that we weren't influenced to get this. But because we blinded, we couldn't figure out what this was until the very end. And we have in our rules that once we unblind, this is we have to publish whatever we get, and this is what we got. So we can actually average these two together to combine the power of our two data sets, and actually we can get a value with a smaller uncertainty by combining these two independent experiments. And because the error bars get a little smaller, that increases the significance of the discrepancy with the standard model. So instead of 3.77 sigma, we're now at 4.2 sigma. So we strengthen the discrepancy with the standard model. Still not 5 sigma, so we still can't claim a discovery, but maybe we're on the way to that. So that's very exciting. This is why this is so exciting. So in the end, my second to last slide. So we confirmed the Brookhaven result. And so what Brookhaven did was confirmed by us. So that means that's correct. We strengthened the tension with the standard model. It's at 4.2 sigma, not 5 sigma yet, but maybe we're getting there. Still can't claim a discovery, but we have a lot more data to look at. Run 1, our first result, was on 6% of the total amount of data that we hope to collect. So we have actually 2 more years worth of data in the can, run 2 and run 3. And now we're actually in the process of taking run 4, and we'll have a run 5, and maybe we'll have a run 6. So we're actually at 10 times Brookhaven now, and we hope to get eventually to 20 times Brookhaven, right? That would be our full statistics. So in about a year, a little more than a year from now, we plan on releasing the results from run 2 and run 3. So these are blinded still. We have different secret blinding factors. So these are still blinded. So we'll look at run 2 and run 3, do those analyses and checks and cross checks, and then maybe in summer of 2022 we'll decide to unblind again, and we'll see what we get. And then, as I mentioned, we're taking run 4 now. Actually, next week I have to go on shift. We babysit. We all take turns babysitting the experiment 24 hours a day. So I'm on evening shift from 4 to midnight for 4 days next week. So it's actually a lot of fun. I'm looking forward to doing that. And so we have a lot more data. So what does this all mean? So you've heard there's been a lot of reports in the news. We've broken physics. You don't have to listen to your physics professors anymore. So what does this mean? If this really were a sign of new physics, and again, not a discovery, but we have hints. What could this new physics be? And the issue here is that this experiment by ourselves, we can't determine that alone. There are models that are compatible with our value for G-2 and are also compatible with not seeing anything at the LHC yet. And we can't tell which of those models are right. The LHC is doing a big upgrade, and they will be able to look at a lot more data a lot faster than they could before. And so, there's hope that they can see rarer and rarer stuff because they're going to be making a lot more data, a lot more collisions. So maybe they'll have a hint of something as well. And so to really pin this down, we need another experiment to have a hint. There are some other hints out there, nothing above 5 sigma. And so, it's still a wait and see. But it's still very exciting to see these hints, and especially the hint from us come out. So don't throw away your physics books. The standard model still works. Where it works well. And we'll have to see where these hints will go, and it's very exciting. If you want some reading material, if you can't sleep one night, you can find our papers. There's a website called the Archive. If you search for this person's name, you'll find our 4 papers. They're very technical, but they're neat, that describe the experiment. And if you actually want something more basic, actually sort of along the lines of what I've talked about, if you Google G-2 explain comics, the American Physical Society has a comic that they've asked this person who makes the PhD comics. He's really good, and he has a comic strip about the G-2 result. Okay, that is all that I have. So hopefully I left you with a sense of how the experiment worked, kind of the history of it, where we've gone and what we've done and where we're going, and some idea of why this is so exciting. So thank you very much.
Thank you so much, Adam. This was an incredible talk. We have, as you can imagine, quite a few questions from the audience, both here and YouTube Live. So I'm going to ask you a bunch of questions from our audience.
That's great. Perfect.
So first question, could there be something systemic in the magnet producing the results, as it's the same magnet in both experiments? Right. Would it have been better to build a new storage ring, or is that a possibility?
Right. So that's a great question, and we've asked that question ourselves, and basically at every seminar we give, someone asks this question. So it's a good question. So yes, the magnet itself is the same, but everything else is new. So the detectors are new, the beam is new, right? The inflector, the different parts of the magnet, the inflector magnet, the kickers, the quadrupoles, those are all new. And we've improved upon the magnet from Brookhaven quite a bit. I mentioned that we made the magnet very, very uniform. We actually did that better than Brookhaven did, about 3 times better than Brookhaven. And so we really believe that there's really no correlation between our experiment and the Brookhaven experiment, even though we use the same magnet. The magnet itself really just supplies the magnetic field, and it has the strength of the magnetic field, of course, is important, but that doesn't necessarily tie the two, our experiment and their experiment together. And basically, to build a new storage ring would have been cost prohibitive. We probably would not have done the experiment. Had the ring fallen off the barge and sunk or something horrible like that, we probably would not have done the experiment because it would have been too expensive to build a new magnet. But like I said, we're very confident that there's no correlation from the magnet itself between the two experiments. Thanks.
Awesome. A lot of questions about the five sigma. How long until? What do you think is going to happen next? There's more runs coming up. What do you see happening next?
Right. So actually, I think I'm not sure if run 2 and run 3 we think we'll get. So that should be a factor of 2 better in uncertainty. Will that we'll be a lot closer to 5 sigma? Will we actually reach 5 sigma? Maybe not. Maybe we'll be right on the edge of it. Certainly, once we get run 4 and run 5, then we should be well. If the result stays the same, of course. If we keep getting the answer where it is, then yeah, I think certainly by the time we're done, we'll be. The plan was to be well over 5 sigma, and so we should hit 5 sigma somewhere along the way. I don't know if we'll get there when we analyze run 2 and run 3, but hopefully shortly thereafter.
Awesome. So from YouTube Live, can this kind of experiment be done with the tau particle?
Oh, that's an excellent question. I'm so glad you asked that question. So, kinda. In fact, if we could do it with the tau, it would be kind of a lot better because I didn't really explain this very much, but the electron, so this experiment has been done with the electron, actually to exquisite precision, to sub part per trillion precision. But the problem is that because the electron is so light, let me see if I can get back to that slide. Whoop, that's not working. Whoop, I don't want to do that. Hold on a second. Where was it? Well, okay, there it is. Okay, let me do that. Okay, so because the electron is so light, it is only really sensitive to certain types of these diagrams. Because the muon is heavier, it's actually more sensitive. So it's sensitive to these diagrams with quarks and the diagrams with the Z and W boson. The electron is much less sensitive to those. A tau would be even more sensitive to stuff. The problem with taus is that they're very hard to make. Well, actually, that's not true. We can make taus. They're not made as copiously as muons. So they are hard to make, and they live for an incredibly short period of time. They live for something like 10 to the minus 13 seconds. And so when you have a particle that lives for microseconds or hundreds of microseconds, that's easy for electronics to deal with. Electronics can deal with things at the microsecond scale very, very easily. But when you're talking about, sub femtosecond, which is, 10 to the minus 12 is a femtosecond, we're talking, faster than that, then that's very, very difficult to do. So no one really knows how to do this with taus in a way that would work. If we could, that would be great, but that would be an incredibly difficult experiment to do.
So we had one question about the data. How is this experiment's data stored? How much data is gathered and how much data is gathered for each of the runs?
Okay, so I'm trying to remember. So I said it was about 8.2 billion positrons for run 1. and run 2 and run 3 have a little more than that. So it's probably, I don't know what the actual number is. I'll guess it's around 10 billion each, maybe a little more for each of those runs. Let me get to that plot again. That's what I'm trying to do here. Oh, missed it. There it is. Yeah, so run 2 and run 3 are quite a bit longer and have a lot more data. So they'll probably have, I don't know the answer off the top of my head, but they'll have, hopefully 30 or so billion positrons. So runs 1, 2, and 3, if you want to know about how much data, this takes about, I'm trying to think, 4 or 5 petabytes of data, maybe more, maybe actually now it's about 8 petabytes of data. So it's a lot of data that we store on tape at Fermilab for this experiment. Hopefully that answers the question.
Yes. So another question, what is your current favorite explanation of the difference between theory and measurement?
Mike, so I'm not going to give you a fun answer. As an experimentalist, we see, actually it's very interesting. The theorists themselves are trying to figure out which models could be compatible, and there are many. I don't have a personal favorite. I mean, supersymmetry would be fun because I was involved in a supersymmetry search when I was a grad student, and there's just a lot of experiments that have been looking for supersymmetry, and so far it's eluded the LHC if it does exist, and so that's sort of been a puzzle. So it would be great if it were supersymmetry, but it would be great if it would be anything else. So I think it's not that I would prefer one or another. It would be great to know, right? That's really what we're hoping for. And once we do know, once we get to the point where maybe the LHC has seen something, or we have a much bigger discrepancy, and other experiments are starting to see hints, and we get a better picture of what the theory is that's beyond the standard model. That doesn't necessarily mean the standard model is wrong. It just means that it's a piece of a bigger picture, and we will have learned more, right? So that's what we want to do. We want to learn more. We know the standard model is an incredible theory. It predicts so many things. I don't have actually here. I will, since you asked the question, I can. So in making this talk, my talk came out to be twice as long as I wanted, so I had to get rid of a lot of slides. So I can actually show you one now. Haha. Okay, I think you can see this one. Mm-hmm. So this is a plot from the CMS experiment. There are many Fermilab people who work on CMS. This is at the LHC at CERN in Europe. And so this is many analyses looking for standard model particles. So that's kind of the dots are the rate that these particles are produced in the LHC or in the experiment. The standard model can predict this, and so the gray bars are the prediction, and the dots are what this experiment measures. And a lot of times you can't even see the gray bars because the dots are right on top. Sometimes the dots are within the error bars. Sometimes the gray bar is below this weird thing here, and this is actually a limit. This is so triple Z, so looking for 3 bosons. That's something the LHC hasn't seen yet, or CMS hasn't seen yet, because the value, the rate that it's predicted is too low, too rare for what the LHC can produce right now, right? So they set a limit. But this whole plot here is 9 orders of magnitude here. This is an incredible plot because basically it shows how strong the standard model is, that all of these predictions are basically correct. So this is an amazing thing. And this is why it's so hard to look beyond the standard model, because the standard model works so well. And even though we have these ideas, we have these things we wish the standard model would do that it doesn't, what it does do, it does incredibly well. And there are very, very small number of experiments like ours, like G-2, that has a hint of something weird going on, right? And no one has a hint above 5 sigma. So yeah. So thank you for letting me show one of my backup slides. I appreciate that.
So a follow-up question to that, how do we know that the anomalous frequency indicates something beyond the standard model and not just a need for some fine-tuning to the thousands of diagrams from the standard model contributions?
That is a great question. Right. So could there be a mistake in or something else going on in the standard model prediction? I don't have it in this talk, unfortunately. So this Muon G-2 theory initiative. Let me find their picture again. There they are. Right. So there's over 100 theorists here. Some of them work alone. Some of them work in small groups. And they've all produced pieces of the standard model prediction. So calculating what these diagrams contribute to G-2. As I mentioned, some of them are very difficult to calculate. And so sometimes they calculate them different ways. And they put all that together. And if you look carefully, you notice that the theory value had an uncertainty as well. So they evaluate all these different ways of coming up with these calculations. And they look to see, how they're slightly different, if they agree, if they don't agree, and they assign uncertainties, we call a systematic uncertainty, based on the level of agreement. And they come up with a very small uncertainty. So this is the error bar that they put on this value, and that takes into account sort of all the different ways of doing these calculations. Now, to be fair, there are some very new calculations that are being done with a technique called Lattice Qcd. So some of these diagrams can be calculated in a new way with this technique. The technique itself is not that new at all, but it's being applied to G-2 in a way that kind of pushes this technique to its limit. And so they're producing, I don't have the plot here, but they're producing results that are more pushed out to the right, but a lot of them have very large error bars that could, basically they overlap, everything. So you can't really say what they're saying. They're not included in this average because they're very new and they need to be evaluated. There is a new result from Lattice Qcd from one group, which is more over here toward the experimental value. And that's very interesting. They are claiming that they understand how their calculation works to a very high level of accuracy, but that has to be scrutinized, and it's very new. And so actually, it was so new that it came out after this value was determined, and this was determined a few months ago. So this thing is so new that it hasn't been looked at very closely yet by the Muon G-2 initiative. So I think they're going to be very busy over the next year. Lattice Qcd does involve a lot of assumptions, and there's some regimes where it works really well, and there's some regimes where it doesn't work very well. And so, if groups are claiming it works very well in lots of regions, that's something that has to be looked at. And this is how science works, right? Someone pushes things to the edge and gets a result, and then it has to be scrutinized by the community. And over time, the community will either believe it and maybe that'll push the standard model value over to the right, or maybe they'll find something that was overlooked or a reason to doubt these new calculations, and it'll stay down here. So we'll just have to see. I think as we're busy doing analyzing run 2 and run 3 and taking run 4. The Muon G-2 initiative will be very busy evaluating these new Lattice Qcd results because they are in conflict with techniques that they've been doing for 20 years. And so even if it turns out that these Lattice Qcd results are more correct, then they have to explain why these long-established results are wrong. What's wrong with them? Because now there's a tension within the standard model that has to be understood. So no matter what happens, we'll learn something new. So I think that's what I want to say in the end.
So what are your thoughts about the possible relationship to dark matter as the news has talked about this? Is it just wild speculation or is it justified?
So I think there's something in between justified and wild speculation, right? So as I said, there are lots of models that are compatible with Muon G-, with our value for Muon G-2 and this discrepancy. Dark matter models, some of them are compatible, so it could be dark matter. It could be other particles called leptoquarks. It could be supersymmetric particles, and we just don't know. Like I said, we really won't. We can't determine that our experiment alone. We need hints from hopefully, hopefully the LHC will start seeing some hints, or other experiments will start showing some hints, or we'll need to have new experiments that are even more sensitive, and maybe that'll point us along the way. So guiding to an answer like that is difficult at this time, but we're starting to sort of shine light on things, and right now the spotlight is very broad, but maybe with other experiments it can be narrowed in the future.
So we have a few practical questions. As the magnetic field is measured every 3 days, how much variation is seen over time?
That's a great question. I can show you this. Where'd it go? Here it is. Right. So that's a great question. So we actually care about the magnetic field where the muons are. And to do that, we have to run this trolley around the ring. And actually, we have a little camera. We can see the trolley go by. It's really cool. But yeah, so the magnetic field between those 3 days does change. And that's mostly because for run 1, we had a hard time controlling the temperature of the Hall. So this sort of shows the changing magnetic field over those 3 days that we can measure with these embedded probes in the ring. And that's really what they're for. So we have, I think, 300 and some probes around the ring. They're fixed in the ring. And they're measuring how the magnetic field changes in between the trolley runs. So the trolley runs are kind of the very precise measurement. And that's every 3 days. And then we use these fixed probes to get from one 3-day measurement to the next 3-day measurement, so we can determine what the ring was doing in that intervening time. So these fixed probes really make it so that we can do that.
Awesome. So when you kick the muons so they won't crash into the ring wall, does this affect their spin? And how do we know things in place to focus and kick the muons into a focused beam are not affecting the results?
That's another great question. The kick is incredibly short. So if it does change the spin, it doesn't change it very much. I don't have it in this talk, but there is actually something neat that happens. So yes, the quadrupoles do change the spin, but we can actually minimize that effect by choosing a very particular momentum or energy for our muons. So it turns out there's something called the magic momentum. And if the muons are going around the ring at 3.09 GeV, that's the magic momentum, then that minimizes the effect of the field from the quadrupoles. It doesn't, so it actually, if you choose this exactly right momentum, then the muons really don't feel they're not affected by the quadrupoles. Now the problem we have is that most of the muons are going, a lot of the muons are going around 3.09, but a lot of them are not exactly 3.09. Some of them are a little off. So there's always a range of momentum. They're very close. They're within, I think, 0.15% of 3.09, but that's enough that we have to worry about it. So we actually have a correction. We can calculate, we can look at where the muons are in the ring, and that tells us what the momentum distribution is of the muons. And from that, we can calculate a correction for this effect. There's actually another correction because the quadrupoles focus vertically. That does set up a little vertical oscillation of the beam, and so the muons might not decay the positrons in the horizontal plane. They might be tilted up a little bit or tilted down a little bit, and that's called the pitch. And there actually is a pitch correction that we make. We can figure that out. And we can correct for that and assign uncertainties to that as well. So those are actually long-standing corrections. Brookhaven did them too, and so so we know how to do them, and we know how to estimate their uncertainties, and so we do all that. So yes, so that's a good question, and we know how to deal with the effects of parts of the ring that could potentially change the spin.
So does the ring make much sound when it's working?
Huh. That is a good. So not really. So you can't be inside the Hall when the ring has muons, because there is potential for radiation, and so we have a kind of a elaborate safety system, an interlocking system, so no one can be inside the Hall. So you can't be in this picture when we actually have beam in the ring. we do, it's kind of funny, like I mentioned sparks. So sometimes some of the kicker plates and some of the quad plates can spark. That's actually not so good. We don't want that to happen. And for the kicker, we actually, sometimes those can be heard. And so we actually have a baby monitor next to the kickers that's tied into computers in the control room. And so we can actually, if the kickers spark, which fortunately is very rare, we can actually hear them spark on these baby monitors. It's really kind of funny. But we have other ways of detecting the sparks as well. It's sort of a backup, last resort way of detecting these sparks. But really on the whole, I mean, there's fans running for all these electronics, there's fans in the hall. So you just kind of hear a hum of stuff. You don't really hear things whooshing around in the ring. But the baby monitor is kind of fun.
So is it possible that the 5 sigma requirement is too high a threshold given the intrinsic uncertainty of what you're trying to measure, as suggested by the standard model?
It's a good question, interesting question. So no, so 5 sigma is really the standard for experimental particle physics. I think it's also for other areas of physics as well. It's a long established standard, and really, you strive for that result. So you try to take enough data, and maybe it takes years to get there, but you do. And I have a slide that actually, well, maybe I won't show that slide, but to try to explain what that means. So basically, what you're worried about is, could the actual value, let me get there, could the true value really be the standard model value? And what you're seeing is an unlucky statistical fluctuation. So it's like, if you're playing backgammon, if those of you who play backgammon, each player, when they turn, they roll 2 dice, right? And if you roll double 6s, you're really happy because that's like the best move you can get. And sometimes when you're playing backgammon and you're playing against someone and they're doing really well and they get like, 2 double 6s in a row, and you're like, oh, this is terrible, you're going to lose. That's really unlikely. It's very unlikely to get something like 2 double 6s in a row, but it can happen. Unlikely things can happen. And so, the less likely it is for that to happen, then the more robust your answer is, right? So basically a 3.7, so actually here, 4.2 sigma means that if in fact the true answer is a standard model, then the odds are 1 in 40,000 that a statistical fluctuation could make your result be pushed out all the way to here. So that's becoming, that's quite unlikely. And the odds of 2 double 6s are like 1 in, I think, 1,200 or something. Yeah, I think 1,200 or 1,300 or something like that. So a lot less likely than the odds of getting 2 double 6s in backgammon. But if this were 5 sigma, then the odds would be 1 in 1.7 million. And at that point, we say, that's so unlikely that then this result is very, very robust. So the closer you get to 5 sigma, the more robust you get. So we're getting, we're better than 3.7, so we're getting more robust. But that 5 sigma really is that gold standard that we want to meet. And that's when everyone takes this seriously as a discovery. And so the Higgs had to be above 5 sigma. The top quark, when that was discovered, that had to be above 5 sigma. And we're keeping with that tradition because that works. Because one out of 1.7 million, that's really rare. Very, very unlikely that would happen. So sorry. Thanks.
So time for one last question.
Great.
So thinking decades ahead, where could this new discovery lead?
Decades ahead. Okay. So hopefully in the next 3 or 4 years, our experiment will be done. And we will, if things go the way they're going, this is a prediction, right? We don't know if this is going to happen, but we will probably get a result which is much greater than 5 sigma, assuming the standard model stays where it is, maybe moves around a little bit because these lattice results, we'll have to see what that happens. But maybe we get a result that's greater than 5 sigma, and that would be great. And as I said, even with that, we alone can't really say what the new physics is. But hopefully, decades from now, the LHC will have run. they will be in a position to hopefully see something new if it's within their reach, right? There are things within their reach or maybe not, and so we have to see what they see. We're doing another experiment here called MUDE, which will be turning on probably in a few years, and they're going to look for a very, 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 very rare decay of the muon, something like at a rate of 10 to the minus 50. And so if they see something, that's a big discrepancy with the standard model, if they measure something above that. And so that again would narrow down the spotlight, right, as to what we see, what models there could be. And we have these big neutrino experiments that are going on, and they're looking for things like what's called CP violation and understanding how neutrinos work to even greater detail. And so this is all this all gets put together, right? So we try to create with all these experiments, try to create a picture, a hopefully consistent picture, and it might not be for a while. This is how science goes, right? It takes a while for things to sort of merge into an answer, and it might take decades to do that. But we have pieces that we're putting together, and hopefully we can do more powerful experiments in the future, based on what previous experiments see or don't see, that will guide us, along this journey to understanding more about nature and the universe. That's really ultimately what we want to do, and maybe along the direction of what this bigger theory is that the standard model we think lives inside. There you go.
Awesome. Thank you so much. And for those of you that did not have your questions answered, or those that are interested in learning more, we'll have a G-2 focused Ask a Physicist or Ask a Scientist on April 25th. And our Physics Slam on April 30th will feature a talk by another G-2 physicist in a very different format. So thank you again, Adam, so much. This was wonderful. And I look forward to seeing everyone here again at one of our other events. And congratulations, what an amazing, amazing, amazing accomplishment.
From all of us at G-2, thank you so much. And this is really a lot of fun, and everyone have a good evening.